Thank you, Lars, and welcome back, everybody. Glad you can make it for another session. So finally today we tackle the elephant in the room called neurofeedback. So I tried to prepare a little bit of groundwork for that, but we can of course revisit the previous concepts while we talk about neurofeedback. And I know most of you know about neurofeedback. You practice neurofeedback. It's not anything new to you. But I want to start from first principles, just so that we see, okay, from what framework would be best to describe this method and how that framework can then inform, efficient applications of it. So today, we're talking about neurofeedback, but I want to start with the concept of where neurofeedback, what's it based on? What's the foundation of applying neurofeedback as a treatment? And that's basically on the fact that on the brain and how brain activity is related to also structural architecture and functional activity and so on. So we have this kind of parallels very much that, the brain is kind of a computational system, and therefore it probably most likely, resembles a computer that we came up with as a machine that, solves a lot of our problems these days. But actually, so one of the ways to summarize, computing, at least current computing, is that the software is kind of like the programs the machine runs, and that's sort of similar to functional activity because it's where all these activities are processed, and that the hardware is kind of fixed, and that's more like a structural architecture of the system. But in the brain, it's not at all like that. We know that, for example, there's new paradigms that are coming out now, artificial intelligence, neural networks that are based on this, kind of inspired by neural networks, real natural neural networks, and that these things are interdependent. So basically, the fact that the software and the hardware is actually interdependent and they impact each other, and these connections between nerve cells as well as these elements of neural networks are actually shifting and changing as the brain learns, or as the neural network learns. So in fact, the brain function and the brain structure are interdependent. We know that through all these changing synaptic connections and so on. So we shouldn't treat it like a computer, and therefore, even the treatments we apply to the brain should really reflect that symbiosis between brain function and brain structure, which I don't think we've really fully harnessed yet, at least not in the current treatments we have, like medication and stimulation and so on. And basically, obviously, that's rests on the concept of plasticity. But so to harness the plasticity, we need to have a way in, right? And then, so if you think that, okay, brain structure is the way we want to long-term change brain activity, but one way in is through brain function, right? Because these two are kind of interdependent. So, but then the question is how best to control brain function. And there's different ways of controlling it, but the simple concept of control is actually been formally kind of investigated using this control theory. So one framework for understanding neurofeedback is control theory. Now I'll explain a little bit what I mean by control theory, but I know a lot of you, and in literature, everybody talks about operant conditioning. And operant conditioning, yes, it is a framework for explaining things, but it doesn't explain a lot because it comes from behaviorist principles that, are merely descriptive on the sort of superficial side of behavior. So you could say, okay, well, in behaviorist, principles is like you reward a particular behavior and you get more of it, or you punish a little bit of behavior and you get less of it. But that doesn't really explain what's going inside the box, right? In behaviorists, actually, they try to almost neglect or even like ignore, cognitive processes that's going inside the brain. So all they say is, okay, what's important is just the output of the system, but what's inside doesn't really regard us, and so it's irrelevant. But what's really key is that since neurofeedback is based on neural parameters, that we understand those neural parameters or neural mechanisms. So behaviorism doesn't tell us anything whatsoever about the neurofeedback, or at least it completely ignores it. So what I want to start with is a very simple system that you're all familiar with, which is your house thermostat. And essentially, this concept of control is based on three principles or three elements. The first is sensing, the second is computation, and the last one is feedback. And how does this all come together to create this sort of control system? So let's say in a thermostat, you obviously have this first parameter, which is the temperature you want to set the room to. And that's so-called the set point. And let's just say here we're in 20 Celsius. I don't know Fahrenheit but basically, let's say you want the room to be at 20 Celsius in the room temperature, but currently the temperature that you're sensing using the sensor of the thermostat is 15 degrees. So you're below this ideal value of 20. So the room is cold. And what the system simply does is computes the difference between the set point and the current value. So that's simply the 15 degrees minus the 20, which would be a -5 difference. And then that would be fed back to the central heating element, saying there's actually an error of -5. And so this loop would be continuously sort of revolving until the error would be 0. So how does that work? Well, since the error is -5, that would be below 0, and that would switch on the thermostat, the central heating, the controller. And then as the thermostat, as the central heating is heating up the room, then the temperature that is being sensed would basically increase. So it would be going to about 16 degrees. And then the error would be -4. And then, as it keeps heating, the error would be -3, -2, -1, and so on. And then it would drop to 0. The error would drop to 0, and then the heating would switch off. And then as soon as the error becomes -1 again, the heating would switch on. And so therefore, that continuous loop, closed loop of sensing and feedback provides the room temperature to be around 0. Okay, so that's a very basic controller. And one way to think about it in the brain is that there's similar mechanisms at play. That basically it's about error detection and how that's related to where you want some activities in the brain to be. So the key issue is that control is successful only for observable variables. So if you don't have a direct sensing, so by observable, I mean by variables that are clearly sensed. So in this case, temperature, you cannot really control that variable. So if you want to control a neural parameter, well, you need to accurately sense that parameter. So for EEG, obviously, you need to have an EEG electroencephalogram that correctly, measures it and that it does it in real time, let's say. So that's key. And of course, you can have like internal models of how some variables are related. But in empirical way, a very good way to do that in real life without any model is to use this kind of control system. So essentially, that's basically the closed loop neurofeedback. And that it starts with, you have a brain state. Let's say that's kind of like the brain temperature. The state can be defined by different measures. But let's say there's some kind of, let's say abstract measure called temperature of the brain or excitability or whatever it is. Then you sense that variable using different neuroimaging techniques, usually non-invasive, but it can be also invasive. So let's say EEG or MRI or whatever it is, fMRI. You compute the difference between that brain state and some feature, you compute a feature, and then you try to see, okay, the current state, how is it related to the feature that you want? And then you trigger back, you give some feedback to the system to control the feature, right? And in many cases, the controller is either an external system or an internal system. Now, when it's an external system, then it's more like let's say the central heating, it switches on, switches off, or it could be an internal system, which is the brain itself, which is what typifies neurofeedback as we know it. But we'll get to that. So you have this brain state, which can be defined by these different task-related brain activities or spontaneous brain activities. And then this loop is going, and then you're comparing that to some set point, which is essentially the computation, and then you can do some intervention on that system, which is so-called neuromodulation, and that can be either extrinsic, either coming from the outside, which is some of these transcranial direct current stimulation, transcranial alternate current stimulation, deep brain stimulation, TMS, transcranial magnetic stimulation, or, for example, another way to do it is using this neurofeedback, which is intrinsic. We'll get to that. So intrinsic is when the brain itself is the controller. So it's trying to learn how to control these different parameters. And here's an outline of my talk today. So we're going to start about what is neurofeedback, intrinsic neurofeedback in this case, and then what's the current evidence base for neuroplastic effects of neurofeedback. So really like very strong scientific evidence, usually controlled for effects of neurofeedback on neuroplasticity, and then how we can leverage those effects to treat disease. So, and then of course, you can also sort of separate these effects into short-term effects and long-term effects. And then, of course, we close with the sort of neurophysiological mechanisms potentially underpinning these plasticity effects and a kind of general and theoretical framework. So we go back to the closed loop, and here's another example of a closed loop. You're all familiar also with cruise control in your car. You set the speed that you want the car to cruise at, and then again we have the same thing. The computer in the car is sensing the vehicle speed in real time. Now, when the vehicle speed is lower or higher than the current speed, it will either let go of the power of the engine, or it will increase the power of the engine. And so the power of the engine is setting the speed accordingly. And again, control is successful for the observable variable of speed, but also the sensor should be accurate and with a high temporal resolution. So you can imagine that cruise control is not going to work very well if it updates the speed only every 10 seconds. It's just going to sort of be up and down all the time, the speed. So to get good control of the variable, you need good resolution, and that's what EEG obviously provides. And essentially what neurofeedback does, the magic of neurofeedback is, what I've already kind of intimated, was that it allows unobservable brain activity to become observable by this fact that you're sensing a neural variable directly through some measure like EEG or so. So you're getting the actual direct measure of the brain activity, and that direct measure is being fed back to the system, and then the system is able to, or tries to, control it. So I also want to underline the difference between the classic similarity between BCI, what we call brain-computer interfaces, that also kind of came to the fore around the 1960s, 70s, and neurofeedback, because these two domains have kind of like developed independently of each other, but they're very similar to each other. So I'm always surprised to see how little communication there is between them. But I think that's also due to the fact that they have different goals. Like they both domains use control of brain activity in a closed loop. So there's always feedback. But the main difference is that in classic BCI, you only kind of concentrate on this control aspect. So you control a particular neural variable, and then you decode it to create a command for something else, like say yes or no when you're locked in patient, or you want to control like a wheelchair to go left and right. But there's no assumed, apart from the control aspect, there's no assumed plasticity in the system. Whereas neurofeedback, there's obviously an aspect of control because you need to control the neurofeedback variable. But on top of that, you are sort of assuming that this control will lead to some plastic altering of the brain activity itself. So the goal is to actually change the brain activity in and of itself, which is different from BCI, where the goal is simply to sort of command or control an external device. So that's what I want to concentrate a lot of my talk on, this plasticity aspect, because the control aspect is important, and we'll talk about control. I've just spoken about it a little bit about control loop, what's key. But I think the first study that I think showed that this plasticity aspect was really relevant for rehabilitation, potentially, as well as plasticity, is this paper by Sturman et al. 1970 that showed that you can condition, activity in the cat. So here it shows a slow wave electroencephalic rhythm recorded from the sensory motor cortex of the waking cat has been correlated behaviorally with the suppression of movement, facilitation of this rhythm through conditioning. This is basically neurofeedback by giving milk to the cat and so on. Selectively enhances a similar pattern recorded during sleep. So the key here is that there was conditioning of this pattern, which obviously increased this pattern during neurofeedback or during conditioning. So that's so-called online. But what's key is that it enhances a similar pattern recorded during sleep. So it's outside of the training session. And the training also produced longer epochs of undisturbed sleep. So it has a behavioral impact. And basically the specific neural mechanism manipulated during wakefulness appears to function also in sleep. So outside of the training. So that's key. So there's some control of this parameter, but it also generalizes outside of that control system. And that's what you can regard as a plastic effect, right? Outside of the control itself. And so the plastic effect can be harnessed in the brain. But, plasticity in the brain is necessary, but we also have both positive and negative effects of plasticity. So in some sense, you can think that the brain has plasticity because it obviously is a positive feature. And that positive feature of plasticity allows the brain to learn new things. Obviously here, learning. Everything we've learned in our life is based on plasticity of the brain. We can also modulate brain activity through meditation. So we can change brain activity by kind of engaging in particular brain activities or behavioral states. And then also, if a particular region of the brain is injured, then plasticity can kind of reroute or rehabilitate that region some way to come back online or restore some function. So those are the positive aspects of plasticity. But of course, with that comes also the sort of the bad side, which is the maladaptive side of plasticity. So if plasticity doesn't go in the right direction to rehabilitate the function, then we can actually lead to dysfunction. So, for example, post-traumatic stress disorder is not a genetic problem per se, but it's something that's acquired through some experience. So in this case, the system has adapted badly, let's say, to a particular one or two events that are very traumatic, and then it is not able to emerge back to how it was before. Or addiction, where it's kind of a positive feedback loop, where this plasticity of the system wants more and more of the substance, and then it cannot break that loop. So the idea of neurofeedback, in essence, is to use this positive effect of plasticity to counteract maybe the negative effects, where either the system has acquired a maladaptive plasticity, or it was not tuned at the beginning in the right way, and then we need to guide it to use the positive plasticity to rewire, let's say, the system to be more optimal. So you probably know this history. I just wanted to review this. This is how many scientific publications have been published on neurofeedback per se, or EEG biofeedback. And we know there was this initial bump here at the beginning around the 1970s, 1960s. And then there was a large dormancy period of very little research during the 80s and 90s. And then this sort of non-linear increase. This is the paper that I already quoted in 1970. Then there's another paper. These were both published in Science, so top journal in kind of neuroscience. But there was very little uptake from these initial pioneering discoveries. And people described to me that, including Barry Sturman, that there was a very little NIH funding. So even though there were these prestigious journals publishing research on operant conditioning and neurofeedback, there was almost like this decrease in the number of publications after that. I started my PhD in 2006, and then from then, luckily, there's been an increase in publications, and now there's been more than that. So that's really promising. But overall, there's been very little research in general in neurofeedback. So there's still very scarce research compared to other domains like TMS and other types of brain modulation techniques. This is just to show one reference that you can look up. This was in Nature Neuroscience in 2017, that I think shows that the scientific community is taking neurofeedback very seriously, and that it is considered a scientific discipline in its own right. So I think there's much more to be learned about it, but I will give you my overview of what we know so far, at least what I think is an interesting lens onto neurofeedback mechanisms. So as I said, in a neurofeedback loop, the sort of intrinsic loop is that the brain itself is the controller, and you have these three components. So sensing, computation, where the computer extracts the feature and calculates it versus something, classifies it, and then you provide the feedback in the visual forms or auditory forms. So essentially, the EEG feature is relative to a target level, and this target level you can consider as the set point of the system. So there's some parallels there between how neurofeedback is implemented and these kind of control loops that I just showed you with the thermostat. So for example, the set point is essentially the threshold that you set during your feedback training. So you can make it lower or higher depending on which direction you want to go. And then this fluctuation of this parameter, relative to set point, is essentially the error. So that's the error that your brain is shown, on a trial by trial basis, how this brain activity fluctuates. And so if you're, let's say you want to increase the activity or keep it above the set point, then as long as the error is not lower than that set point, you're getting positive feedback. And the system is kind of saying, continue doing that. But if that loop suddenly, the error drops below the set point, then there's negative feedback given to the brain as the controller, and then the brain has to come up with another strategy or another brain state to live up to that set point that it's setting itself, or that you're setting it. So essentially, it's a closed loop, and then obviously there's some visual feedback that kind of re-represents that error in a more sort of fun way or a more motivating way. But essentially all the system is doing is trying to either be above or below the set point and find the brain state that corresponds to that. And when it's receiving negative feedback, that's essentially the error being fed back. And so it's trying to minimize the error by getting most positive feedback, as much as positive feedback, as little as negative feedback. So, of course, it's not easy to control many different brain states, and that's still under research, which brain states or which brain measures we can control. But overall, there's a lot of evidence showing that the brain can learn to do that. And so it is kind of like a thermostat system that is conscious of its own activity and can regulate it. And if you think about probably like any kind of learning that the brain does, that's a little bit of what it does in general. For example, when you play the piano, you get an error because you press the wrong note, so you change your behavior according to that error. And so all learning, trial and error learning in the word itself is based on this negative feedback loop where the error gets fed back. And if you get the right thing, then you get positive. So, and essentially that's what you can do with neurofeedback on some measures. So here, let's talk just about control without the plasticity aspect. So let's say there's some resting state activity here. There's beta amplitude being fed back. And the goal is to upregulate beta. This is a study by Kropotov nicely showing this. So you can see the white blocks is the kind of rest blocks, and they have their own internal fluctuation. They're not always constantly the same beta, but it is kind of fluctuating between 5 and 6% relative power. But then during the training blocks where this kind of control is being fed back and you're saying, okay, you raise the threshold to be higher than the rest value, you can see clearly that the training blocks have a much higher amplitude than the rest blocks. And then as the feedback is not provided again, like during the rest blocks, the activity goes back down. So it's kind of like a control system where the idea is to simply increase the signal relative to the noise being the natural fluctuation of that parameter during rest or during spontaneous activity, and the control being the transient change of the signal, either higher or lower than this rest value. And so what's necessary for neurofeedback to be effective, or the first like sine qua non, is that the change during control is different from the rest value. Otherwise, the system is not really changing. You're just continuously repeating the spontaneous state. So you need to have some kind of a manipulation there where this value statistically, let's say, the distribution of these values is a different distribution from the spontaneous values. Otherwise, you're not really changing the brain state. And if you're not changing the brain state, then why would you assume there will be some plasticity there in some direction? That's different from the spontaneous state. We'll talk about that later a little bit more. So I want to get to the evidence so far in some studies. There's a lot of studies, so we don't have time to cover all the neurofeedback studies, or not even half of them. But some of the kind of exemplary studies are showing plasticity effects. And I'm going to start with short-term effects. Why? And then there's also different measures you can use apart from EEG. Because if you just say, oh, I can show you plasticity with EEG, well, that's kind of a little bit of self-fulfilling prophecy. Well, of course, you're changing EEG and then you show me that the EEG changes. But is that really a measure of plasticity? Because in many cases, neuroscientists don't consider that only a measure of plasticity. So there's some other measures that you can use that have been used with TMS and fMRI. So we'll get to those. But the reason why it's important to show short-term plasticity effects, in my opinion, is because most of the evidence that we have in neurofeedback is using many sessions. So, for example, in healthy subject, you use like at least 8 to 10 sessions of neurofeedback. Or for clinical applications, you need these effects that are kind of very nuanced to accumulate over time to have kind of overall big effect. It's a little bit like trying to see, okay, is there an effect on muscle strength immediately after one training session at the gym? Well, usually if you want to demonstrate changes in muscle strength, you would do many sessions. But the question is also, is there an effect that's tangible within only one session or after just one session? Because in fact, using other types of brain modulation techniques like TMS or TDCS, they can show these changes even after one session, and it's tangible enough. So before this study that I carried out in 2010, there was no real evidence that one session neurofeedback was tangible in terms of plasticity, that you can detect it. So we asked ourselves, can you actually detect even one plasticity after one session neurofeedback? And of course, this depends on the protocol. what measure you're changing, can the people learn to change it significantly to really translate this activity into some resting state change or spontaneous change, plastic change later. But we had it a go, and basically the classic paradigm to do that is to use TMS. Now, TMS is this magnetic coil. This TMS refers to transcranial magnetic stimulation. So it's through the cranium, through the skull, and you stimulate using the magnetic field, and then you measure the activity on the muscle, because there's this sort of corticospinal tract that is kind of proportional to the excitability or the connectivity of this system all the way to the muscle. And that's the motor cortex going down to the spinal cord and the spinal cord down to the muscle. So this is a sort of a setup that neuroscientists have used very often to look at changes in plasticity as well as excitability. And there are ways to modulate this pathway. So I'll just go back to what this actually means. So TMS stimulation of motor cortex evokes muscle activity. So this is this trisynaptic pathway going from the motor cortex down here to spinal cord to the muscle. And what you're really recording is this motor evoked potential, which is the twitch of the muscle on the hand. And the size of this twitch effectively is measured by this MEP, the motor evoked potential. And the size of this motor evoked potential indicates how strong the twitch is. It's kind of like an EMG measure, but more temporal resolved. And this size is proportional to the strength of this pathway. So if you change this pathway somehow in terms of excitability, then this MEP will be modulated at the muscle. So if, for example, the pathway is stronger after an intervention, then this MEP should be larger in size. And you, of course, you take many measurements of the MEP, and then you average across. So let's say you take something like 50 of them. You stimulate 50 times using this magnet, and 50 times you measure here at the muscle, and then you average the average size of these MEPs. They fluctuate depending a little bit on brain state, but on average, they should be higher or lower, whether you've changed the system or not. So they've used this kind of a setup to, for example, probe the effects of drugs on on cortical excitability. So you're probably familiar with diazepam. It's a benzodiazepine. It's usually classed as a sedative. It calms the nerves. And that has GABAergic action. We know that from the receptors that it stimulates. And that actually lowers the MEP size. So that's not surprising. It lowers cortical excitability. On the other hand, psychostimulants such as methylphenidate, which are so-called agonists of noradrenaline, they actually enhance motor evoked potential. So there's a question here: what is the psychological experiential significance of cortical excitability? Well, basically, it will behaviorally make somebody more behaviorally active, but behavior is not the only or not the direct way to assess it. I know, Glenn, you've asked this question before about whether arousal is a good model for neurofeedback or sort of what protocols to apply to the brain. But behavioral arousal is not the only or not the best measure, I would say, for that. Because, for example, in ADHD, you have hyperactivity, so you have motor hyperactivity. It could show that the motor cortex is more excitable, obviously, because they're moving. So with excitation, it's usually linked to kind of activation of that network. But the actual, upstream cause of that hyperactivity of that motor network might be disinhibition. So, for example, the frontal cortex might be inhibiting the motor cortex, and that imbalance might lead to this hyperactivation of the motor cortex. So, for example, you could have, so what I'm trying to say is that if you have inhibition of an inhibitor, so if the prefrontal cortex is considered inhibitory in some relationships with the motor cortex, then loss of that inhibition might create disinhibition, which means activation of the motor cortex. But the main problem is the frontal cortex being hypoactivated or hypo-excitable relative to the motor cortex. So it all depends where the chain of causality is. And just because you see one measure of excitability, especially behavioral, doesn't tell you that on the EEG that might be the case. So as we know in ADHD, There are some cases of them having higher excitability or patterns of higher excitability or hyperactivation, but it could also be that they have patterns in the frontal cortex that are patterns of delayed maturation or lower excitability, or like having higher theta and so on. So the reason why I want to talk about this is because, yes, excitability is a good measure, but what I mean is that you should have it as a neural measure, not as a behavioral measure. So when you say somebody is excitable behaviorally, that doesn't tell you anything about their cortical excitability per se. I think so. You can see here these substances have a general effect. We know that psychostimulants, if you take a lot of them, you might be kind of hyperactive, but it could also be that if you take a psychostimulant and you suffer from ADHD, that you're actually calmer. So this is the point. So enhancing excitability can also lead to behavioral calmness. So the two are not really directly correlated. Okay. Of course, sedatives will make you more sleepy. I think that's usually a given. But the relationship between brain and behavior is sometimes complex. So I want to stick to the neural parameter. That's why we said neuro and neurofeedback. So what I want to say is that this MEP here is lower when you have sedatives, which supposedly suppress excitability of the motor cortex, and stimulants increase it. Now, we also know that the functional state of the sensory motor systems also dictates excitability of the system. So it's another measure of how excitable the system is. And what they've done is they looked at when they stimulate the motor cortex at different phases, functional sort of activities of the motor cortex, which you can basically capture with the EEG. What does this MEP look like at the outer end of the system? So if I stimulate with this TMS pulse during phases of high alpha or low alpha, for example, here, you see here EEG band amplitude. Well, if the EEG band amplitude of alpha is high, then it actually translates to a lower motor evoked potential. And when this alpha is low, then there's a higher motor evoked potential. So essentially, at least for the alpha band, not so much for the other bands, as you can see, there's no major difference between red and blue for the other bands. Alpha is the best one for the sensory motor cortex to differentiate higher versus lower excitability states. And that's in line with the previous slides I've showed you, where alpha has been shown to inversely correlate to cortical metabolism. So as I said, when the alpha is low, the gate is open, the system is kind of excitable, it can process sensory information coming into it. That's both the case for visual alpha as well as motor alpha and also auditory alpha. In this case, we're talking about motor alpha. So alpha needs to lower alpha levels are linked to higher motor evoked potentials. So they're most like if you kind of given a methylphenidate to the system. Now, this is a study where we conducted to look at whether modulation of alpha power using neurofeedback can impact cortical excitability as well as plasticity. So the two are kind of equivalent here. Plasticity means a change in some neural measure long term. So we wanted to change this cortical excitability, the motor evoked potential, and we measured it before and after neurofeedback. And we applied a down training protocol to the motor cortex with neurofeedback, and we asked people to decrease alpha power during neurofeedback. So in this case, this was the design of the study. It was a single session of neurofeedback for 30 minutes. We captured these motor evoked potentials in the left and the right motor cortex. We then did 3 minutes of resting state EEG to capture the kind of baseline EEG signature. So we both had a baseline MEP signature, a baseline EEG signature, and then we did neurofeedback for 30 minutes. And then after that, we repeated the same thing twice, actually. The first 15 minutes after neurofeedback and then after 25 minutes of neurofeedback. So this would be sort of considered immediate plasticity or long-term plasticity, or at least up to 25 minutes, which should correlate with excitability. So what we found was, firstly, that you need to prove that you actually modulated this alpha measure. So you can see here's the alpha resting state measure at the left hemisphere, which is where we provided neurofeedback from. But the untrained one was kind of passively being recorded, and that one also changed alpha. So both hemispheres kind of decreased alpha. Our intention was just to modulate one. We didn't really put an inhibit on the other. We just let that co-fluctuate. And you can see that in both cases, the alpha in both hemispheres decreased. So that kind of led to an increased excitability in the system because of this inverse relation to alpha excitability. And that was maintained. So these little stars give you the statistical significance versus rest. So rest being up here. So pretty much most of these periods of 3 minutes were significantly lower in alpha than the resting state value. So the neurofeedback, let's say, was successful. The question is what happened pre to post neurofeedback. And so what we found that on this motor evoked potential measure, which is normalized by 100 being the baseline value before neurofeedback, so increases in that would be increased excitability. You can see here immediately after neurofeedback, the value was actually the same. So immediately after neurofeedback, there was no change, but this excitability increased with time. Now that's very curious and interesting because if it was a simple arousal effect because you were doing the task, then you would probably think that the curve will go like this. We would start with high excitability at the beginning because you sort of got excited because of the task or whatever. And then this excitability of the system would go down as arousal wanes further away from the end of the task. But in fact, we found a positive correlation between the excitability increase and the elapsed time after training. So here at around 25 minutes, we had the highest effect in excitability, which was around 30% on average across all subjects. Some subjects had double the amount of the MEP, basically the MEP doubled. Some had lower effects, but on average, we had a 30% boost in this measure. So that shows directly that there's some change in the after neurofeedback. Now, we also wanted to see, was there any more correlation, for example, between the changes during neurofeedback and so on. So we determined this correlation coefficient, which was how the alpha power changed over time during these 10 periods of 3 minutes. And essentially, the good learners, so kind of the good controllers, they had to decrease, right, the alpha. So that would be this sort of C would be the ideal case scenario. But of course, some people maybe didn't change their alpha at all. That would be the case B, or maybe even increase their alpha, which would be case A. So then we looked at that correlation coefficient and then correlated that correlation coefficient with the changes in the MEP for each subject. And we found that the more negative the correlation coefficient, the higher the MEP increase across subjects. So again, gives us more confidence that actually this translation of the increased excitability was related to those ones that actually control their EEG mostly in the negative direction of alpha across time. So that was a nice demonstration that, you know, these things are coupled to the actual neurofeedback performance. And also we looked at the resting state alpha amplitude change, since the alpha should also, you know, relate to the excitability of the system when you're measuring with the MEPs, when you're basically stimulating the system. Because you're not stimulating during your feedback, you're stimulating after, during the resting state. And we found that, you know, of course, again, in line with hypotheses, the less alpha people had post neurofeedback, the higher the motor evoked potential. So in some sense, we're modulating the activity during your feedback, but then that translates onto the spontaneous activity, and that spontaneous activity then explains the change in the motor evoked potential that's recorded during that spontaneous activity. And that is exactly what we found, this three-way scatter plot, where training EEG correlates with resting EEG change, this meaning change here, delta. And that resting EEG change also correlates with MEP. So three ways. So there's a three-way correlation between these three variables because they're kind of correlated between each other because it's part of the same effect. In fact, you can model that as a structural causal model. And so this is what it basically infers, is that the training EEG that you modify online correlates with the resting state EEG. So you basically modify the resting state EEG post neurofeedback via this modulation, online modulation. So online changes correlate with offline changes, and these offline changes then translate into a motor evoked potential change. And this direct route, which is directly training the EEG to as a correlate of the change in the MEP, which was actually significant, you know, in this three-way scatter plot. You can see it here where the training alpha is correlated negatively with the motor evoked potential. That actually disappears in significance if you take this other route, which is this model here in the red, the indirect path. So that basically suggests that the best model to understand neurofeedback through, at least in this experiment, is that the neurofeedback impacts the resting state, and then that resting state has the best correlate with the excitability change using multivariable potentials. So that's something to bear in mind, that you need to have online changes, but those online changes probably impact the spontaneous activity, at least if you're measuring spontaneous activity excitability of the system later on. This is interesting also from the point of view of other types of techniques that are used to modulate excitability in the brain. Now, excitability in the brain is important. As I showed you, medications impact excitability significantly. So psychostimulants will increase it. So in some case scenarios, you want to excite the system, and then that leads to improvement in symptoms. Or you might want to depress the system and kind of calm the system down because it's overactive. So sedatives can decrease, as I said, these motor potentials. Now, TMS can also be used in a repetitive fashion to kind of stimulate the system. And if you apply it for in trains of 1 hertz, that means once a second, you actually have an inhibitory effect. So you see here this negative change. So you can actually decrease the excitability of the system using 1 hertz TMS if you apply it for a long enough duration. Then if you increase the frequency of this stimulation, you start to excite the system because you somehow entrain the neurons to fire very fast. And you can see here, if this is the entrainment frequency, and this is how long you need to stimulate for, otherwise it might get dangerous. So if you stimulate at 25 hertz, you can only apply it for like less than a second. Otherwise, there might be some seizures and so on. So, but overall, they've done experiments on this type of intervention, and they found that on average, for example, at 20 hertz, this is the average excitability gain that you get with these kind of interventions that are, let's say, extrinsic brain stimulation. And then I actually took the error bar of the effect size for neurofeedback and the effect size here, which is the average effect size. And you can see here it overlaps quite nicely with the effect size that is usually seen after these very powerful, let's say, electromagnetic stimulations. So in some sense, it's all this to say that actually, even if you stimulate or if you entrain the system to do it endogenously, like using your feedback, the plasticity of the system will yield in that direction in a strong enough effect, at least for this protocol based on alpha, to increase excitability as much as a kind of an electromagnetic stimulation. So that's, in my opinion, quite surprising and shows that your feedback has actually a really strong impact on the brain, at least for this protocol. And if you overlay the effects again also on the effects of TDCS, which is transcranial direct current stimulation, it's another type of brain stimulation that isn't rhythmic, but it's kind of like depolarizes the cells to make them more excitable. So anodal usually increases excitability, cathodal usually decreases excitability. Again, these are kind of effects that try to emulate also medications. Now, you can see here, there's many graphs here, but this is essentially, they start around here, and then the effects either last longer in time or they sort of drop out. But the effect with TDCS is about 50% above the baseline. So if you stimulate for some time for large strengths, current strengths, then some of these effects last for 50 minutes post-stimulation. So for example, here, so this curve here, 50, that's after 50 minutes of stimulation, this excitability is still enhanced, okay? But on average, the stimulation excitability increases about 50%. And again, if you overlay the neurofeedback, then we tested here around 20 to 25 minutes. So the top part of this error bar overlaps with the top part of this, or like the middle part of this TDCS. So again, it overlaps with the classical other types of therapeutic agents that can be used to change excitability. Now, I showed you that alpha down neurofeedback can enhance excitability significantly. The question is, can it also decrease it if you do alpha up, for example? So for example, we're in this territory here. You can kind of simulate the psychostimulant effects by increasing excitability, which I would say mechanistically might be similar to giving a psychostimulant, at least on the motor cortex. but we don't know whether, for example, increasing alpha might lead to sedative effects, or we know that increasing alpha usually relaxes people. It's been associated with lower states of arousal, or at least calm states of arousal. So it will be interesting to do the study, but instead of decreasing alpha, increasing alpha, and then conversely, because of these mechanisms of inverse relationship between alpha and excitability, if you successfully increase alpha, then maybe you would have these kind of depressing effects of neurofeedback, such as what diazepam would do. But that hasn't been sort of validated yet. Did you train eyes closed or eyes open? Eyes open. Yeah. They used visual feedback. So that's much more research needs to be done. But you can see here alpha at least being some kind of a direct relationship with these excitability measures that can have some clinical sort of implications. Now, let's get on to another study. I'm probably going to run out of time here. There's quite a lot of studies I want to cover here. But let's go quickly through this one. This one is based on the fMRI networks, based on the relationship that some networks are related to sensory processing and also internally versus externally oriented states. Now, previously I told you that alpha is a kind of a gate for external sensory information, especially visual information. And then the question was, can you enhance these externally oriented states using alpha neurofeedback? Now, externally oriented state means you're sensitive to kind of visual information, and you're also suppressing internally oriented states, which are kind of like thinking. And usually when you're thinking, I'll explain this later, why alpha goes up. But if you think about it, it's something like, well, the alpha amplitude is here. And if the alpha amplitude is high, I told you the gate is up, then this is kind of an internally protected state where you're thinking, mind wandering. And when the alpha is low, then the gate is open and you're receptive to external stimuli, and that's when you're very attentive, visually at least. And so you try to see whether you can modulate this rhythm. So instead of having alpha down training in the motor cortex, you're now doing it in parallel areas. So that's based also on this evidence here, where they looked at simultaneous EEG fMRI studies and showed that especially this alpha topography like this here that has this maximum and PZ is positively linked to this default mode network. You see here negatively linked to visual areas. That's not surprising, but also positively linked to default mode. And default mode has separately been linked to a behavioral state called mind wandering. And so when people mind wander in the scanner, then this default mode network seems to be co-activated, and it's the same network here that you can see the voxels overlap with this system. So in some sense, if you connect these two, then changing alpha here would also change default mode here. So that was the initial hypothesis, and also change mind wandering. So overall, the hypothesis was that if you downtrain alpha, you would decrease default mode network activity, and that would also decrease mind wandering, because those three are positively linked. Okay, positive correlation here, and then negative correlation between default mode. Actually, this is wrong. This should be positive correlation. I thought I changed it, but this should say positive correlation between alpha and default mode. You can see here, positive here, red, and red here. So anyway, those three are positively linked. So down-regulating one of them, i.e. the alpha, would suppress both mind wandering and default mode. And so this is the protocol, reducing alpha powered PZ, one session of neurofeedback, short-term plasticity effect, and we had two groups, one real neurofeedback, one sham neurofeedback. Sham being just a repeat of somebody else's session. So they did an attention task where we assessed the mind wandering, during which also we did fMRI, that's the baseline. They came out of the scanner, they did EEG 3 minutes resting states, then we did 30 minutes neurofeedback similar to like the TMS design, and then we did, again, repeat the same thing once after outside the scanner, both resting state EEG and the attention in the mirror. What we found was that actually people can downregulate alpha very well, similar to in the motor cortex. You see here they start off around 17 whatever microvolts, and then they drop the alpha during the first training period, and then they keep the alpha low. So here we have almost perfect control of alpha power based on attention, because we asked them, what did you do? They said they just paid attention to focus attention on some visual stimuli. And the sham group, interesting, does drop because they're paying attention to the feedback, but there's no contingency there, so they start to creep up with the alpha power, and it's also very, very large variability of the alpha power. So if you do a correlation coefficient across time, then the neurofeedback group has this nice negative correlation coefficient, and the sham group has a positive correlation coefficient. So technically, these two brain states induced are different between the two groups, and we find that also topographically, although feedback was provided only at PZ, you can see here that the alpha power decrease is much lower during neurofeedback than versus sham. There was some slight difference in beta power, but this was the main target. And when we correlated the changes in training alpha, so here training alpha being normalized, so-called percent change, normalized by the baseline power, so negative changes being in the direction of training, the preferred direction of training, and then changes also in resting state alpha, I think that's also normalized by the baseline value. So here, this is the pre to post change, pre to post neurofeedback, that one session. You see there's a nice positive correlation. So those subjects that decreased alpha the most during neurofeedback were also the ones who decreased it most after neurofeedback. So that's really an EEG evidence that there's plasticity in the system, and that's globally actually. So although alpha was provided by parietal regions here, that also was the case for the other alpha in other electrodes. And that was actually surprisingly not the case for sham, surprisingly or unsurprisingly, but you could think maybe some changes of alpha during this sham feedback here, you can see that change. Some actually decreased alpha during feedback, some kind of went around zero, but it did not translate into this resting state change. So I think this shows very nicely that neurofeedback, at least in one session, can impact the resting states, whereas the sham doesn't. And this is controlled for the reward rates, because the sham got a similar reward rate, the type of stimulation, because the sham group also received the same sensory stimuli, the same video game was played. Plus, they were also engaged in cognitive control. In most cases, they didn't know it was sham. So this shows that there's some specificity of the control parameter that then translates to a resting state change. And behaviorally, we found this nice positive correlation with mind wandering. So less alpha post neurofeedback in the resting state, less mind wandering in the task. So there was decreased mind wandering during the task, and that wasn't the case for the sham group. And then finally, because of this hypothesis we had with the default mode, this was also confirmed. So because there's a positive correlation here, you see here positive correlations is for correlations with default mode in this precuneus regions of the default mode network, we found positive correlations. That means less mind wandering, less default mode network activity in this voxels here, and also less alpha post neurofeedback, less default mode network activity there. So in some sense, this protocol can be used to downregulate default mode activity as well as mind wandering. Maybe not on the group level, but for those ones that did show good control, by diminishing alpha, they also had diminished resting state alpha post neurofeedback as well as diminished mind wandering post neurofeedback. Which, So overall, this fits with this model of sensory attention, where the sort of behavior degrading, i.e., default mode network that's involved with mind wandering is anti-correlated to this salience network, which is the dorsal ACC plus the insula. So when we looked at these PCC or precuneal regions, they were downregulated. And then actually, we also found that this other network that we didn't really hypothesize was going to be upregulated was actually upregulated. So the salience network in these frontal dorsal medial regions, dorsal ACC and the middle mid-cingulate were actually regulated in terms of connectivity. So this is kind of an indirect effect of the neurofeedback that maybe also increased this control network that is involved with suppressing the default mode because during sensory attention. So the implications for that is essentially could be on disorders that have default modes network increases. So did you check what happened to the other frequency bands? Maybe the whole EEG spectrum went down when alpha went down. I think we checked the other bands. I don't think there was as much specificity as there was with alpha. Although that wasn't part of the hypotheses, and you would have to then justify why you looked at the other bands. But yeah, I think the effect was the largest for alpha for sure. But overall, since alpha is the best band that correlates to default mode, at least in some of the other studies, it could be a target for mental disorders that involve default mode network that we know indirectly are impacted in, for example, depression because of this excessive rumination. And since default mode network is linked to mind wandering and rumination and so on, and sort of internal self-related activities that are not to do with kind of external attention. This study here, for example, showed that the functional connectivity of the DMN, especially these PCC and preclinical regions, are actually hyper connected compared to controls. And there's many papers on default mode network being hyper whatever connected or hyperactive during sort of depression disorder. Not in all depressives, I think, but at least in some of them where you might behaviorally see a lot of, let's say, internal activity, like restless thinking, racing thoughts, and a lot of internal thinking, then this protocol could be useful for that. But again, it has been only demonstrated on healthy subjects, so I think there's a lot more research to be done on that. That's one impact on another type of plasticity. Now, that's kind of metabolic connectivity, right? Now, what about long-term plasticity, and as well as other types of clinical populations? Because so far I just showed kind of effects on healthy subjects. Let's take an example of ADHD. You're probably familiar with this, but let's start with the best kind of researched clinical disorder with neurofeedback, and that's childhood ADHD. I showed you already previously that these bands, theta alpha, whether it's slowing of the alpha peak or considered actual theta activity, I think doesn't really matter here what you call it, but you can see here clearly that the ADHDs have much higher power. This is during attention, not just in the resting state. So they're not able to suppress this activity, and especially in adolescents that have more alpha power. That also shows you the alpha power is nicely suppressed during tasks. In typical children and in the ADHD children, it's much more variable. There's less control over the alpha, or the theta alpha. So the early studies that showed high theta, for example, in ADHD at resting state, these are those famous Lubar studies in 1995. They show that pre-training, for example, you see these high theta beta ratios before neurofeedback, and then what they showed is that post theta beta training with neurofeedback, that actually there was an impact on these resting state values where they were decreased, right? So that goes in the direction of normalization. Now, the main sort of takeaway from this study was that the poor regulators, ones that didn't demonstrate online control of the theta beta ratio, their resting states pretty much remain the same post neurofeedback as pre neurofeedback. See there. So no plasticity induced. Whereas the ones that did regulate the theta beta ratio online, so-called good regulators, good learners, they showed this plasticity. That was probably the first study to show that. And there were also differences behaviorally. So although you can claim some placebo differences or maybe even developmental changes over time, because the study took some time, there was some improvement in attention score in these poor regulators, but the ones that really had the biggest changes, improvements in clinical symptoms, were actually the ones that showed this plasticity effect. And they were also the good regulators. So that sort of stimulated, obviously, this field to try more neurofeedback studies in this domain. I will quote only one, although there were a few other ones like Monastro studies and so on that showed similar effects. This one, I think, is, in my opinion, the best evidence because it's the largest sample. It's 102 children with ADHD, 36 sessions of neurofeedback. Also, it was there was a comparison group of sort of attention training that was not neurofeedback based. And overall, they found 0.6 effect size, which is considered kind of medium to large in the neurofeedback group, using theta beta neurofeedback in children. What's interesting in this study, I think, is more the post-analysis, where they actually found that the change in the theta pre to post neurofeedback around the parietal cortex, so PZ, I think, was actually positively correlated to this clinical score change. So you can see here that the lower the theta post neurofeedback, that would be this area here, the lower the greatest improvement in the clinical symptoms. So negative changes here means improvement in clinical ADHD. So that basically indicates that theta amplitude after neurofeedback predicted a decrease in ADHD symptomatology. And what's also interesting is that actually the baseline value also predicts that. So here you have a negative correlation. That means that the higher the theta at baseline, so these would be the most pathological, let's say, children, or the highest normal relationship to the protocol, because the protocol is to decrease theta beta. So they had very high theta here. They're also the ones who have the greatest changes. And if, for example, your theta was, let's say, normative, which I'm assuming is around 10 here, and in fact, you don't really benefit from this protocol. So again, showing that you should, the best effects are for the ones that where that biomarker is the most abnormal, and changing that marker towards the normal levels, like here, actually is correlated to clinical effect. So overall, that means that maybe not everybody with ADHD will have high theta in the first place, as you can see here, and those are also the ones that do not improve. And so we shouldn't necessarily apply the same protocol to all the children to demonstrate clinical effects, because we're washing out those effects that are significant, for example, here, with the ones that are not significant, so for example, here. So it goes to show that maybe we should pre-select the clinical population based on the biomarker to enhance the effect size. And that maybe that's why some of these negative studies on ADHD showed null effects with neurofeedback. There's just one theory. Importantly, these effects also lasted 6 months later without intervening training. So that shows some long-term plasticity effect, very long-term, 6 months follow-up with no training. I think that's amazing. And I think there is a case to be made that the similar approach can be used for autism spectrum. So here, autism spectrum have this kind of inverse U shape. So actually U-shaped compared to normal children. So here again, delta theta is higher. But for example, the beta is, like usually in ADHD, the beta is lower, and the theta is higher. Here they actually have higher beta as well. But in this study, for example, with neurofeedback that I'll show you, they try to just suppress theta. And that's another signature that's been shown here before. So basically theta and beta are higher in the study. This is versus control. So actually red means less in controls. So here, blue means higher in autism spectrum. Okay, so higher theta, lower alpha, higher beta in autism. And what they did in this study here by Kudjizer, they applied multiple sessions of neurofeedback, and they found that across session, you see how the theta power is decreased. So I showed you a single session effect in some of my studies, but here it shows you across many sessions that this effect actually accumulates in the direction of training. So the theta power goes down incrementally with time. And there's a couple of patients for which it doesn't work at all. Interestingly, there are also the ones with the highest theta power, so maybe they couldn't implement the online control enough to really create plasticity in the direction of training. I'll be interested to know whether they even had online control, but they also have the highest theta, so they were probably the most severe cases. And in this cohort, they actually showed improved executive function post-training, post 40 sessions of neurofeedback. And also showed long-term effects after 12 months. So more evidence to show that these effects are actually long-lasting and pretty much the same as after training. So that's really reassuring. Now, one model of that, as I showed previously, is that these resting state dynamics are somehow shifted from highly synchronous, which would be related to this increased theta power on the x-axis. So synchronization is very high or too high for the norm in these patients, ADHD as well as autism, and that the neurofeedback basically suppresses the synchronization and somehow decorrelates the neurons to become less synchronous, and then that brings the system towards more intermediate levels, and therefore that's the therapeutic, behind the therapeutic effect. So that's one way of looking at it. And we've also talked about this, written about this in this paper here in Frontiers, which is open access, where you can have a look that somehow, patients are trapped in this maladaptive, let's say, pathological state, and that as you rewire the system, it somehow falls back into this optimal, healthy state where the system is reconfigured long-term in a better state, and a better optimal trade-off between the synchronization and desynchronization. Have a look at that paper. But overall, I want to now talk about neurophysiological mechanisms that could support these effects. Like, how is it possible that all this is magically done in the brain? Because I think it's pretty much magic that you can change these patterns just simply thinking in a different way, or like putting your brain in a different state, and training this over time, and then somehow you end up with a different brain and you have improved symptoms, right? I think that's the key. Like, we can describe this in terms of behaviorist principles. As I said, we can say, well, you kind of promote more of this brainwave pattern, and somehow it's magically then generalizes offline. But how are these things possibly explained by what we currently know from neuroscience? Well, the first one is, again, this link between brain structure and brain function, right, that I explained before. And so there must be some underpinning in the brain structure. Somewhere, something in the brain structure has to change. Now, I don't think that's very easy to correlate, because these changes in brain structure are not directly related to brain function. We can only image these fiber pathways using MRI, and these MRI changes are not directly related to EEG. We know from this study, probably the only one that's looked at changes in white and gray matter pre to post neurofeedback. This was in healthy subjects. We can see some evidence for changes in these structural pathways. I don't think it's very easy to correlate these changes with behavioral changes, but at least there is, incontrovertible evidence that there are most likely white matter as well as gray matter changes structurally to the brain after neurofeedback training. How those changes are related to actual functional changes is another matter. I think it's very clear. But what's clear is that there is this interplay between functional changes and structural changes, and that's indicated by this study here. But how could we try to relate that? Here's one model, and I'd like to use previous slides because this is why I set it up that way, that it's accessible to you from previous slides to the new mechanism. So I've already showed you how EEG activity is related to neural synchronization, and just to reiterate again, asynchronization is related to decorrelated activity, synchronization related to correlated activity, synaptic. Now, how is that potentially related to plasticity? Now, all this is kind of pretty much the similar side of the same coin, because as I showed you, correlated activity occurs during these windows of excitability. And so these synaptic activities, or even the spiking of the neurons, which are these little dots. So when there's more dots clustered, that means these neurons are all spiking in a similar way or in a similar window. They're related to the phases of these local field potentials, which are essentially what generate the EEG. So during different phases of EEG, there's more or less clustering or spiking. And that's what I already showed you, that when the spiking is coincident in time, then the field strength is large and the power is large. So all this to show that essentially the spiking activities occur during particular phases. So here again, during the alpha oscillation, spiking occurs during this phase. And the larger the power of the rhythm, the more this spiking is correlated between neurons. And I don't know if you've ever heard, but there's a principle behind correlated activity and plasticity that's called Hebbian plasticity. And it goes by this dictum that neurons that fire together wire together. So that's the first part of the principle, that correlated activity, that means fire together. So you see these is phase synchronized activity. So if the phases line up between two neurons, then that would produce higher power, firstly in the EEG, but it would also mean that the spiking activities would overlap in time, and they would coincide in time. So the fact that these, during high states of power, the spiking activities are more correlated, and if that's the case, then they should also, according to Hebb's rule, wire together. Okay, so intrinsically, more states of higher power would kind of imply further down the road more connectivity between those kind of activities. And more connectivity structurally would then also induce more power. So basically, the same kind of patterns would generalize outside of that activity. So essentially, driving the system in correlated activities like higher power would then engender further of that kind of activity. It's kind of self-reinforcing statement, but that's how Hebb's rule works, is that correlated activity leads to the same activity further down the line. So that's why it says neurons that fire together wire together. But that's sort of intracellularly related to this thing called spike timing dependent plasticity. That's the technical term for it. Spike timing, because the spike timing here is in a very tight window where these spikes can occur, and since they occur in the same window, that's when they wire together. If they wire in a different window, if they fire in a different window, then they don't wire anymore. And that's exactly this second scenario, which is still termed Hebbian plasticity, but it's in the other direction where neurons that fire apart wire apart. So here, these windows don't align, and therefore there's decoupling, structural decoupling between these cells, and therefore that leads to less power or less synchronization in the long term. So you can imagine that the previous model I just showed you, the neurons that fire together, wire together, that would be how, if you train up a particular synchronized pattern, let's say alpha, and you're training it up, then that's the mechanism that leads to higher alpha cross sessions, and we'll get to that. And in this case here, this would be the case for ADHD and autism, where you have higher synchronized activity, right, here. But you're trying to desynchronize it during training, so there you have less power. And then desynchronizing it means that these excitability windows between the spikes are less coherent or less aligned in time. And then that actually decouples or structurally disconnects these cells from firing in that rhythm, right? And then that gets translated over time to less and less rhythm over many sessions. So that's called spike timing dependent plasticity, and pretty much the main mechanism that's used to explain plasticity in neuroscience literature. Now, I talked about upregulation. So here's a nice study. I showed you a nice study of upregulating, downregulating theta. In this case, it's upregulating alpha. So you see here is the resting state. And this both shows the activity across sessions. So there's 5 sessions here, but also within sessions. So here we start with this activity at baseline. It enhances, the person is relaxing, whatever, learning how to increase alpha. And then at some point they stop, and this is the baseline change after. So you can imagine that's like a short-term plasticity effect. But you could even call that maybe neuromodulatory. But then, of course, the person goes to sleep and comes back the next day. This value here is slightly higher than this value, but it still continues to rise, and then it drops again. And then here, there's not that much transfer. But you can see incrementally, if you did a regression fit across all the 5 sessions, it's significant. And so this activity accumulates in some kind of plastic way across time, both within sessions as well as across sessions. But you can see that the change across sessions is not perfect. So they don't end up exactly the same starting point. There's some loss there that the system wants to go back to baseline, but there's some slight difference here between beginning of session 2 and beginning of session 1. And that's how this plasticity gets accumulated. These patterns get accumulated across time. And the way you can imagine it is through a closed loop. And what's actually happening is that the fact that you're changing this activity online, you're somehow driving the system to change its state, and then somehow that state change impacts the set point. Now, what do I mean by that? So I told you about the thermostat and the controller here, that being the sort of the central heating. So you can imagine that, let's say I'm driving the system to increase alpha power. So alpha power is a certain level, let's say 20 degrees, but now I'm driving it up to 25, I don't know, plus 5 Celsius or plus 5 microvolts higher during the online training. And so I'm pushing the system beyond the set point originally that it's at. the set point being the spontaneous state. And so I provide a new threshold, a new set point, and say, okay, here, drive the system at 25, and that makes the loop go around. So now the set point, the sensor is, sensing 25, and that's the new sort of activity of the system. And then as the system is being driven to a new set point, there is a new set point being instilled after much training. So in fact, I start off with a spontaneous set point of 20, but then in the end, I end up with a higher set point. So in fact, by driving this activity, you can kind of reset the set point. And that's basically the idea of neurofeedback, is to change this spontaneous activity to a new set point, right? Whether it's higher or lower than the starting point, but usually in the direction of training, right? In the direction of the normal values. So you can imagine that neurofeedback is a process of two effects. The first being the control of the signal online that's driving the system during the training, but then overall the plasticity of the set point, which changes in the direction of training long term. So it's this plasticity of the set point, which is the Hebbian bit, which allows the system to be changed long term. And then therefore here I have identified the plasticity of the set point here, these red points here, where this set point is being changed. And then overall, if it falls here, that would be significantly higher than here. And it's the same thing if you're down training. So it's Hebbian, again, because it's in the direction of training. There is another nuance to this story that I will talk about in the next session, because there's not enough time, this so-called homeostatic plasticity. That's another mechanism in the brain that we can talk about. It's important, but for the classical interpretation of how neurofeedback impacts patterns in the direction of training, this is the main theoretical model that's supported by neuroscience. So yeah, I think I finish here, and we have some time for questions. I didn't cover that many clinical studies, but I think the mechanism is similar in a lot of them. Of course, I think in next session we will talk more about clinical implications or clinical approaches for different disorders by basically looking at those biomarkers that we set, or at least are covered in the last session, and then see how you could get there with neurofeedback and what the evidence is for that. But a lot of them I already covered, and some of them there haven't been a lot of studies. Basically, like for example, schizophrenia, there's been very few studies with microstates or even theta and so on. So we can discuss this now in retrospect also if you want. So if you have any specific questions about this framework. I know I also have some questions from Glyn that are still outstanding that I will cover. So here it says, Glyn is asking, what other protocols demonstrate this short-term plasticity, one session that you showed with alpha training? I don't know of that many. I think there is one study with theta beta by Heinrich et al. That looked at I think across 2 or 3 sessions, not maybe one session. Sorry, but there's not many studies at all with only one session, let alone one session and then another type of rhythm. So let me know if you find that any that show this short-term plasticity effect. I've tried to do these studies because there's kind of direct link in time that doesn't allow for these changes over time. But of course, the overall many sessions is critical to have clinical effects. I don't think you can demonstrate clinical effects with one session, to be honest with you. Would you expect other protocols to show if it tested? Yeah, I think in theory, if the effect is large enough online, I showed you that. No, I don't think it's something special about alpha. I just think alpha is easy to control. And, the change that you get in alpha is quite remarkable. It's probably one of the most, let's say, reliable signals in the brain, at least for EEG. So, for example, if I show you these changes in alpha, you can see here, it's a massive drop from about 17 to 10. So if you can demonstrate such a change short-term or online in another parameter like theta or, I don't know, microstates or whatever, then I would assume that through having plasticity, you would probably pretty much make an impact on the brain of the same amount. But then, of course, it depends what the other measures that you're looking at. What do you think of the use of mental strategy along with feedback? Will it help learning? How do you conceptualize the role of mental strategy in your neurofeedback framework? Yeah, so mental strategy is important if it's explicit. So sometimes, so the point is that you need the closed loop to learn, right? So, but let's say here with beta, you might have a mental strategy that increases signal to noise. And I don't know if it's something, thinking about something or whatever, or being activated, then that would, if you have a mental strategy, that's kind of a more like an open loop application, because you know exactly what you need to repeat. So open loop means you're sort of doing a particular behavior, but you, regardless of how, you know, what feedback you get, you just continue doing it. So if, I mean, you obviously need a neurofeedback to tell you, okay, it's working, but once you know that that's working, then you don't necessarily need the feedback per se. So for example, there's the famous transfer trials in neurofeedback where you don't provide any neurofeedback and you're looking at, can the person control? So if the person can control in the transfer trial, that already means that that strategy has become kind of explicit, and it's very easy to maybe even reproduce outside of neurofeedback. So like at home without any EEG equipment. So obviously, if there is an open loop strategy, like for example, people who use alpha down, they know that they need to pay attention. They can kind of be independent of the system, but I would still say that closed loop at least gives you an indication for sure that you're going in the right direction, you know, whether the strategy works or doesn't. So it's definitely a good sanity check. And I wouldn't necessarily do neurofeedback without the neurofeedback bit, because you don't know where you're going. So it's definitely important for there to be a sanity check there. But of course, then if you don't use neurofeedback, then it turns into a little bit like more like the meditation domain, that you do some kind of open loop things. You produce a particular brain state or cognitive behavioral state, and you're assuming it has this neural correlate. So yeah, it's kind of, meditation is a little bit like neurofeedback, but without the closed loop, let's say. Hopefully that answers the question. What else? I have a few other questions I've here noted down from Glenn. One of my big questions I was hoping the course would answer, I don't know if you can see my screen. Let me see if I can share this question. You share, yeah, I think you can see my screen. So here's the question here on words. Does the arousal model stand up as a rationale for particle selection in your feedback? Is there a more accurate neuroscience-based rational model for particle selection? And let's assume we're not dealing with medical conditions and that we don't have an expected QG system for assessment, but simply for channels of EEG, as is the case for me personally. I sort of tried to answer that question before by saying that behavior isn't the neural state. So you could have maybe hyperactive behavior, but you think that this neural activity is going on, but maybe it's not. So I think the arousal model, what I understand what you mean by arousal model, is arousal model based on behavior. And it's very often there's kind of inverse U relationships between arousal and some neural parameters. So I think since it's inverse U, you could be on either side, and you won't really know which side you're on, either behaviorally or, for example, take kids, they're tired, but they'll be hyperactive just before bedtime. That shows that they're very aroused, but they might actually be now coming to the fatigue phase of the day. So you see what I mean? It's difficult to infer what is happening in the brain. What's most important, I think, and I know a lot of people try to avoid QG, but I think that's, since it's neurofeedback, it's based on neural correlates, and it's based on normative, selection of normative values. It's important that you know which side of this normative spectrum you're on. So either you're too much, so I would say the synchronization model is a much more accurate model. You're either over or under synchronized compared to some parameters. Synchronization being linked to order disorder in the system and entropy. It is also correlated with excitation inhibition balance. Not always, but let's say alpha usually is the synchronization of alpha, even though it has this inverse U curve with arousal. It can be correlated with excitation inhibition, so you can explain some of the effects of alpha uptraining or downtraining with synchronization with excitation inhibition, but it doesn't necessarily mean always the case, right? Somebody who's asleep might not have alpha and they're under aroused, and then engaging alpha wakes them up, let's say. But the opposite would be true for somebody who is higher, very aroused, like awake, and then you increase alpha, then you would actually relax them. So again, you need to know from which side you're coming from. Is arousal upstream from functional connectivity? No, I would always say that the neural measures is always upstream of any behavior, because the brain generates behavior. So it's very difficult to say behavior is upstream of anything that's neural, simply because the flow of causality is from the brain to the behavior, not the other way around. Although there's, obviously circular kind of simultaneous loops. But so I would just say that, there was this interesting question once about why do neurofeedback in the first place? Why can't we just use behavior in a closed loop and forget about the neural bit, right? And that's kind of also a very behaviorist interpretation. Well, if we get a particular output behaviorally, that's what we want. And then why do we even have to go straight to the upstream version of the brain, or what is the source? And I think there's a case to be made for that in some applications, actually. For example, there was this ADHD study that showed they used a control group, EMG control group, and they found that the EMG control group, they asked children not to move, and every time they would move, the EMG signal would be higher, and they would give them negative feedback. So they actually asked children to be immobile as much as possible based on negative feedback from the EMG, and they found that the clinical effect size was pretty much the same. I think it was Strauss group in Germany as the neurofeedback based on theta beta. You could probably think, okay, well, it's not surprising that you get an effect clinically because you're punishing, let's say, you're giving negative feedback because they're moving, and movement is controlled ultimately by the brain. So as long as you capture one part of that causal network, you're going to train the whole system. So you'll still create brain changes or changes in ADHD symptoms, even if the output is just behavioral, right? And as long as the output is, as I said, temporally specific to the behavior as well as accurate, and which EMG is, then you get an impact in a closed loop of that control variable. So if you're dealing with hyperactivity symptoms on their own, maybe not inattention, but let's say hyperactivity only, then EMG biofeedback could be equally as good as neurofeedback. And why not? The question is, what about all the other things that do not have a behavioral output or clear behavioral correlate? For example, ruminating thoughts, depression. Yes, we can see them being behaviorally suppressed, but you can't really train that. You can't just say to somebody who's depressed, just get out of bed, start running. Actually, in some cases, they do that. There's some treatments. They say, okay, start to do some activity. But again, if you want to do it in a closed loop, it's more difficult. Or let's say, I don't know, auditory hallucinations in schizophrenia that have a particular neural correlate in the temporal lobe. There is no behavioral correlate that you can capture here. So going to the source of the brain may reveal the sources of particular, cognitive states that do not have clear behavioral correlates and that are intrinsic, to the person. So I think, therefore, there we could leverage neurofeedback much more. There would be a bigger rationale for that, and that includes a lot of psychiatric disorders, actually. As we know, psychiatric disorders are disorders of mental health, and behavior is not such a clear relationship.
Tomas, there was a question earlier on, and you may have covered it and I missed it. But we get a lot of questions about Alpha Down protocol. Arlita, I wonder, did you get your question answered? Did you want to ask it?
Yeah, I didn't hear anything about alpha, sorry. I have two more questions here, but if there's one more
You're still muted, Arlita.
That's probably why I didn't hear it, because it was muted. Okay, so I will cover Arlita's question first, and then we'll get to the other ones. I wanted to know more about the alpha down protocol with the default mode network. What was the protocol? So the protocol was to suppress alpha power, so just alpha down training, 8 to 12 hertz at PZ. based on this link between alpha and the default mode network and default mode network and mind wandering. And so that was like the initial link we made indirectly between alpha and default mode, for which there is some evidence, simultaneous EEG, MRI, but there weren't any real studies linking alpha with mind wandering per se. So this link with mind wandering was like through the default mode, where alpha is positively linked to default mode and default mode positively linked to mind wandering, and therefore alpha should be linked to mind wandering, right? And actually, behaviorally, it sort of makes sense because during inattentive states or during attentive states, alpha is low, mind wandering is low. And when you're usually thinking alpha is high, it's been shown that when you're retrieving information like memory, alpha is usually high, and that corresponds to kind of mind wandering states. So the idea is that if you suppress alpha, you keep this gate very sensory attentive through any kind of sensory stimuli, whether the feedback is visual or auditory, that as long as the alpha doesn't allow to pop back up, because that would mean internal states, that would improve attention. In fact, that's what we saw. We saw reduced reaction times to some of these mind-wandering stimuli. When we asked people, are you mind-wandering or not? And they basically honestly answered when they weren't. They were actually faster at answering that question, as well as they also reported less mind-wandering when the alpha was low, post neurofeedback. So overall, based on behavior, this protocol would be, let's say, but again, with the caveat that it's based on healthy subjects, it would improve mind wandering. Decrease mind wandering, or decreased, internal mentation or ruminative thoughts and so on, because you're not able to ruminate when the alpha is low. Essentially, that's kind of the antagonism there. That's usually created in the brain. So it's either the brain is externally attentive and it's quiet, and it's not thinking about what it's thinking about, or it's externally inattentive, which means it's mind wandering and it's thinking about stuff, and therefore it's not aware of its environment. Of course, there's a caveat to that, because in PTSD we found a very different thing. We didn't really relate it to mind wandering, but in PTSD, which we'll cover in the next session, we found that patients with PTSD had very low alpha. And so that doesn't correspond with the fact that their mind wandering should be very low. And this is exactly a good example of the fact that the behavior doesn't relate to the electrophysiological type. Because if we had this nice correlated, direct positive correlation between mind wandering and alpha, then in PTSD, since they have a high mind wandering or very high inattention level, they should have high alpha, but that's actually completely the opposite. They have very low alpha and they still have inattention. And so it's because there's an inverse U relationship between alpha and mind wandering, not just a positive one. And basically what it means that at very high arousal levels, behaviorally, the alpha is very low, but that can still lead to racing thoughts because the system is not in the optimal zone, and it just basically the flipping between the attractors. The attractor of the alpha is very shallow, and then it's essentially too noisy, the system. So the entropy of the system is very high because the alpha is low, and that leads to this disturbed thinking. So it's better again to think about it more like hyper arousal, but as well as very low alpha being abnormal compared to the mean. So here it says, what was the protocol? All my clients have alpha deficit. So the classic protocol would be to increase alpha, right? Because you want to, if you say to me alpha deficit, I'm assuming that you looked at the QEEG and you saw very low Z scores, negative ones, right? And so the traditional instinct is to increase alpha, and that's what Peniston-Kolkovsky studies have shown, that if you increase alpha in alpha-deficient patients, especially those with PTSD, that you would restore alpha, they would be more relaxed, and things would go back to normal. And that is, I think, a good way to go. The only outstanding question is, can they actually increase their alpha? Because the problem is that people who have an alpha deficit are very difficult to increase their alpha because they can't relax. And so what I will cover in the next session, which I don't have time for right now, is to show that even if you go in the opposite direction by decreasing alpha, in many cases you can recreate an alpha rebound, which is the homeostatic system saying, I'm going too far with this alpha and I'm going to try to restore it, which is counterintuitive, but there is such a thing called homeostatic plasticity in the brain, because the brain doesn't want to go forever in one direction, because that would be silly, right? If you would be able to go forever in one direction, then you could either create very highly synchronous states like epilepsy or very low synchronous states like PTSD just by decreasing alpha. So usually the homeostat in the brain, including sleep, usually keeps these activities within a particular normal range, which is optimal and which most healthy people operate in. And even if we go further than the norm, it will somehow bring us back. But the assumption is that in psychiatric disorders, this homeostat is somehow lost its self-tuning ability or doesn't really know where the edge is, and that it's stuck somewhere on one or the other edge. And that somehow then your feedback perturbs the system to bring it back, either in the direction of training or with this homeostatic thing where it's like an elastic band and you stretch it too far and it somehow snaps back. So these are, again, theories about how it works, but you could, I will talk about the alpha rebound next session, because it requires literally 30 minutes, I think, at least. Yeah. So, but again, the alpha, yeah, the next session will be dedicated to the EI balance, excitation inhibition balance. So far I've talked about synchronization and all these things, but alpha has a particular relationship with excitation inhibition balance based on this inverse correlation with metabolism. And that's why I think it's also an interesting way to look at things when you find patients with more or less alpha. I'm talking relative alpha, not absolute alpha, because absolute depends on a lot of things like skull thickness and so on. But other measures are, you really do need a kind of an empirical way to judge, is it too high or too low? So yeah, there are always non-regulators. How can we avoid? Do you have any suggestions? Well, what are the difference between regulators and non-regulators? A few studies looked at that, and what they usually found, unfortunately, is the ones that have, for example, there's a few studies showing that the good alpha up regulators are actually the ones who already have high alpha power. So that's maybe unfortunate, because for those that have very low alpha power, as I said, maybe they struggle the most to increase alpha. So already when you're in that state, you're able to promote it, because let's say you're relaxed, you have high alpha power, so you can relax more. And so to get onto the opposite state is more difficult. And that's why this homeostatic effect is interesting. But so far, most studies have shown that if you have a particular pattern, that's why you're good at controlling that pattern in that direction, or at least based compared to the mean. So yeah, so how can you avoid the alpha non-regulators? Well, you can't. They're simply there in the population. Maybe they're in clinical cases, and then maybe you can try to move them towards the mean in the classical sense. But if that doesn't work, then maybe you can take a homeostatic route where you go in the opposite direction. At least that for PTSD, that's the case. Now, I don't want to be presumptuous and say this will be the case for other disorders. I think we need to still find out. Clinically, you can explore that with maybe particular, potential side effects. I don't know. With PTSD, we didn't find any. But one way to, maybe usually to desynchronize the EGI, to suppress power is more easy. I think, at least from a behavioral point of view, than to increase it. It depends also on the rhythm. For example, frontal midline theta might be easier to increase, actually. But I don't know. I don't think there's enough research to show particular brain patterns are easier or less easy to control. Also, don't generalize that only one session is enough to be able to tell whether somebody can learn a rhythm. There was one study that looked at SMR control, and only the 10th session or something were they able to differentiate learners from non-learners. This is a Birnbauer study. For whatever reason, I don't know, it took them that long to learn how to let go, whatever it is. But it can take at least 5 to 10 sessions to determine whether somebody's a responder or non-responder in some cases. But of course, we would ideally want everybody to learn in the first session. But I think that's probably one of the main disadvantages of neurofeedback compared to the other therapies, is that it does require the person learn and cooperate for an extensive period of time, and then maybe find out that they're not able to respond for whatever reason. But yeah, there could be other biomarkers that could be learned that are more easy, but I think there hasn't been a lot of research on other markers. For example, microstates could be an interesting one, but there has been literally no clinical study with microstates yet. So that needs to be explored. And then there's a whole domain of connectivity that hasn't been looked at all. I think there's only 1 or 2 studies with connectivity. Clinically, I think there's even fewer. So I'm happy to also find out if you know of any studies or any anecdotal evidence about different measures being more or less easy to control. But for every measure, you need a sample size of 20 to 30 people, and then they kind of compare them to sham or another biomarker. So yeah, we don't know much about that at all. So I'm going to go to another question. I think here by also Glyn. You have a slide showing the correlation between EEG power and metabolic activation as measured by fMRI. I'll just finish Glyn's question here and then we'll get to this one. So somebody said, thank you. Okay. It showed that even beta, for the most part, accepting high frequency beta gamma has an inverse correlation, suggesting turning up beta is not necessarily activating. Another slide showed beta also goes down in attentional task. So beta being defined in this case by up to, I don't know, 50 hertz, I would say. I know some people consider 40 plus gamma already, but I would say that the cutoff is usually around 60 hertz for this correlation between gamma being positively correlated to fMRI or not. So let me get to that slide right now. I have it here in the first one, I think. I'm going here, and I think I had the slide here somewhere. Yeah. So can you see the slide here? So you see here the frequency is not clear because it's in logarithmic. But this here low gamma that has a positive correlation with bold, and beta has rightly shown has a negative correlation. This slide here is more clear. So for example, here during attention, see this whole band almost 3264. So I think the cutoff is somewhere around 40 something, or at least 40. So if suppressing anything below 40, it is so-called squash. And that's also where most of the signal to noise ratio is of the EEG. And that's reliable. So suppressing everything below 40 is kind of activating. And it's true that only promoting beta doesn't necessarily mean it's activating per se. Beta has a special quality of being linked to GABAergic activity, GABAergic cells. So what you're maybe doing is not necessarily increasing activation, but you're maybe stimulating GABAergic sort of interneurons that have this beta resonance. So that could also be why it helps with ADHD, but it's not necessarily activating per se. Now, of course, it's also about the ratio between the other bands. So if you're activating beta and maybe suppressing theta, there's some kind of special relationship there, although it might be difficult to do that with both at the same time. So that theta-beta protocol is quite difficult to do. Usually I would stick to one band, but of course you can do combinations. I don't think there's enough evidence to say one or the other is better. But of course, the more variables you introduce into the equation, the more difficult the control will be, I think, I'm assuming, because you're adding error into the system, the more variables you include. So you multiply the error of each of these bands as you combine them in some sense, or at least the fluctuation, not maybe the error, but so we try to stick to at least one measure, but of course it could be that some kind of multidimensional quality is also easier to control. But so far, I don't think there's too much evidence for that. So I hope that answers the beta question. Yes, squash protocol, if you want to just arouse the brain or increase excitability, then yeah, anything below 40 sort of down would make sense. Maybe delta here, look, if you look at delta, there's no delta here. This is stops at 4. So I don't know, I think squash protocol should also stop at 4, at least based on this data. Yeah, any more questions? Today we're surprisingly early.
There was one other question, clinician Leanne Hershkowitz. Often clients with trauma find QEEG-guided neurofeedback makes their symptoms worse, not better. Do you think this is from lack of understanding of changes caused by trauma or other factors?
Yeah, okay, I find it. So often clients with trauma find QEEG-guided neurofeedback makes the symptoms worse, not better. Do you think this is from lack of understanding of changes caused by trauma or other factors? So although I advocate QEEG-guided neurofeedback based on the models we've shown, I also said, I think at the end of last session, that we don't know whether these abnormalities, at least mathematically defined, are causal, right? They could be simply correlative. And there might be multiple abnormalities. Now, until you intervene, by definition, you won't know if they're causal or not. So therein is the problem. You have to intervene, but you don't know whether the intervention will work. So unfortunately, the job as clinicians will not become easier unless there will be large sample replicated studies in the future, which is what the idea of clinical trials is. That we try one approach on this group with a clearly defined biotype, run the protocol, see, okay, this protocol in this direction based on this QG parameter works or doesn't work. So the idea is that we do all this somehow, globally or scientifically, and then see if it's reproducible, and then, hopefully it will be replicated in the clinic. Now, since you're more on the edge of exploration, and for the moment we don't have these clinical trials, you're kind of stuck with this experimenting. But I don't think there's any way to know in advance whether a particular clinical variable is causal. Now, I don't know what you mean by QG guided feeder specifically. Is it based on theta, alpha? But I would say that if they are not responding, that probably that variable isn't related to the symptoms, or maybe it could be, again, I don't know, it could be that going in that direction towards the norm somehow destabilizes them. Maybe ultimately it might be stabilizing, but it could be that the process of doing it isn't ideal for whatever reason. Of course, trauma is a complicated disorder. It's not just, let's say, one pattern or another. It's probably a lot of different things at once. So I have obviously no magic recipe for how to make things better in trauma. We know that arousal is one dimension of trauma, and that alpha neurofeedback helps with arousal. But again, that could be just only one subcomponent of trauma and not the main component. So yeah. There's another question. I use alpha down frequently with good results. Okay. So when you do alpha down, you do it in patients with trauma. Patients with low alpha or high alpha, or you don't know. Trauma mainly. Okay. So yeah, the work we've done with Ruth Lanius seems to indicate that this works, which is very surprising based on the QG model, let's say, because as I said, most patients with trauma have low alpha, and suppressing alpha further doesn't make sense from this Hebbian or normalization point of view. But then if you introduce homeostatic plasticity, then it does make sense. So I think there's exceptions to the rule. And I think it's what works best, what they can control. Do you think training alpha up or down is different whether you do it eyes open or eyes closed? Usually training down would be more easy with eyes open, because you're kind of focusing on something visual, and that usually suppresses the alpha further. And with eyes closed, maybe up would be better with auditory. I mean, that's what the Camille studies were usually based on, auditory feedback for alpha up. But I don't think there's been any explicit comparison between different kind of eyes open versus eyes closed for regulating alpha. I don't know any research on that. But yeah, that's intuitively what I would think would be easier. I mean, most of our alpha done study, all of them were based on eyes open states. I think we answered most of these. But yeah, I think we'll come full loop, full circle next week with the homeostatic stuff and applications potentially of that. But again, this is still quite novel. There is some research that indicates that could be the case also with ADHD, that there's this homeostatic stuff that I can present next week. But otherwise, I think, yeah, in terms of models, synchronization is a good one, because that's the thing that seems to be most respected in the brain. I mean, in most cases, but yeah, there's always exceptions, I guess. One new message. Is there any evidence about overtraining and the homeostatic response? Not that I know of, but I think the best person to ask that would be Ruth, and shoot her an email, I would say. Maybe she's seen some abreactions. I know in this randomized control trial, we didn't report any, so I'm assuming there weren't any. But overtraining, if you define it as, I don't know, an abreaction or a negative side effect, then that could be, yeah, of course, concerning. And overtraining, I think, is also meant by, maybe having secondary effects like a headache or something like that. That's maybe mild as a secondary effect, but might not be what you want in the clinic. The homeostatic effect is something where you see the activity going in the opposite direction of what you expect. So, for example, if you're doing alpha down and you're training alpha down and the person's successful based on their resting states to decrease their alpha, but I don't know, let's say 15 minutes into the session, you see suddenly them generating a lot of alpha, which is counter to the effect that they had initially, then that might already indicate that within the session you're getting some kind of homeostatic rebound or homeostatic counter effect. And maybe that's already the point at which you could stop or at least take a break, because it indicates the brain is not really responding, plastically or neuromodulatory in that direction. So you already kind of triggered a response, and then maybe that's a good time to stop. And then if you don't, I don't know, but I'm assuming that maybe that would lead to headaches or whatever, something. Yeah. I find clients get quite tired, eye fatigue, headache from training longer periods of time with alpha down. Yeah, exactly, with as little as 12 minutes. Yeah, so actually, because alpha down is kind of activating, it requires quite a lot of effort to keep attentive, and that usually further excites the system. You don't really want to go beyond the point of the person being uncomfortable and like making a lot of efforts to do it. So as you wrote, maybe even 12 minutes is enough. And then, of course, as the system gets more stamina, because they're becoming, let's say, more healthy, they might be able to do it for longer, right? But if you see that at 12 minutes or 10 minutes, they're already starting to produce a lot of alpha and they're getting fatigued, that also gives an indication that possibly the system is already on the edge, and then you just push it a little bit and then it starts to, get this homeostasis going on. So for those people, homeostasis might occur much earlier than for normal healthy subjects. We have more stamina or more, let's say, room at the bottom, or whatever you want to call it. Yeah. So 5 minutes left for any more questions about any slides that I presented, especially if they were not clear. Here are the slides again. I don't know if you want to cover anything in more detail. You can see my screen. There's my screen. Yeah, I have slides here from the talk. What protocols make sense for optimal performance training? From Glenn. Well, it's a complicated question based on the fact that what performance you want to optimize. So in some sense, you would need to know what does that task or that performance, what EEG patterns make that task optimal. So again, I come from more like a data-driven point of view. I'm not assuming that a particular performance, let's say ballet, or let's say, I don't know, fighter jet pilot, or whatever it is, golf putter. All those three activities similar in terms of what the optimal EEG pattern should look like or not? It could be that, for example, if you want to optimize creativity, that's not going to be the same as optimizing attention, for example. We know that from neuroscience. So first you have to decide what is it that you're optimizing, or define what is it, what kind of behavior we're optimizing. And then we can say, okay, this activity of the EEG is closer or not to that performance. But if we had to, like, push me to say, okay, what is the best state to be in for any performance in general, or like the one from which to depart from, this is the model here that I just showed in the slide. I don't know if you can see it. And that's why the brain is poised in this middle area of synchronization. So the resting state, if you take the QEEG as the average of all the resting states of all people without brain problems, then that tells you that's the state that the brain should be tuned at to be optimal, at least in the resting state. And then, of course, you can say, well, maybe the resting state of the general population isn't optimal for a particular task. But for all intents and purposes, that's the middle range within which we are kind of the best at everything we want to do, in some sense. Which, again, we can say, well, the normal population doesn't indicate anything. But it's the one that can then be used to visit the lower one or the higher one. So it's the kind of, let's say, the most flexible one to be in. Whether that optimizes the performance or not is another matter. You could obviously be a little bit closer to this side if, for example, you want to be highly attentive. Let's say you want to be highly attentive, and you want to have low alpha, right? In some cases. So maybe not being here in the middle, but slightly over here would be better, just before a task. Or maybe you want to be more creative and you want to have higher alpha. In some studies show that higher alpha is linked to more creativity. So then you would want to be a little bit more on this side. But then again, as I said, it depends on the task you're trying to optimize. And we don't know enough about particular tasks in general that, you can do an EEG study separately and find out, okay, this is what patterns usually look like. And there's a few studies with alpha and creativity, you can look them up. So for example, for creativity, more alpha usually is better. For kind of any internal mentation process, more alpha is better because you can block out the distractions. And inversely, for any kind of attention tasks, like detecting stimuli where the brain should be very quiet, where the default mode is off, then lower alpha should be more beneficial. And so it's also, you can ask the person, like, oh, if they're struggling with attention or keeping on task, then usually that would indicate higher alpha. But again, as I said, usually the ideal way to do it is to do a QEEG and find out what does the alpha look like in the resting state. Is it higher or lower than the norm? Because if the person had a trauma and they have lower alpha, then I don't think lowering their alpha further would help necessarily, like, unless you do this rebound thing. So that's where it becomes complicated. So he says, maybe neurofeedback works as a hormetic stressor and doesn't matter what particular neural state you train. Maybe it's about flexibility, being able to go up and down in alpha. I wouldn't disagree with that statement because, as I said, this middle state is about alpha going up and down. The point is, how do you achieve the state? Now, if there's some kind of protocol that you're going to do up and down that's going to, improve them being in the states, in the middle states, although you don't really know where that state is, and somehow the brain self-tunes automatically to that state, then yes, you can kind of hope that will be the case. But it's always good to have some quantitative measure to do that, which is the QEEG to confirm where you are at. But yeah, if you don't have any of those means to check, you need to say, well, up and down, up and down. But with the caveat that you don't necessarily induce plasticity just by going up and down. For example, take an example of the spontaneous state. The spontaneous state goes up and down all the time, but only for a brief moment at a time. And that's how it conserves the homeostatic state that it's in. Now, what you really need to do to perturb that state is to keep it high for a certain amount of time, according to Hebbian plasticity or homeostatic plasticity in the other direction, but perturb it for long enough for something to be triggered that says to the system, I want to move in that direction or opposite that direction, but not just maintain the spontaneous state. Otherwise, doing nothing would be equally as good, right? Or go up for a certain amount of time, let's say 5 minutes, and then go down for 5 minutes, but maybe not alternating up and down sequentially every trial. I don't know. I mean, I know there's these protocols like slow cortical potentials where they try to do positivity, negativity, and they seem to work, but I'm wondering whether if you do it in blocks, it might be more efficient. But I don't know. I mean, it's just based on plasticity principles that if you want to do something, you need to do it for multiple trials in some direction to get an effect. So yeah, that's there should be some comparisons, hopefully, in the future where they do alternative training in different directions, maybe like within the same session. But my prediction would be that if it's within the same session, then it might not be as good to induce plasticity than if you do it on separate sessions. But yeah.
Great. Thank you, everyone, for coming today.
Yeah, thanks, everybody. So Glenn is asking, you said 5 minutes. Do you think that would be good to try? You could try 5 minutes up, 5 minutes down. The question is, are they going to be good in both directions the same way? So if it works in both directions equally, then that's why not? Or you could do one session one day and then another direction the other day. I don't know. I mean, nobody's ever tried this. Good, great. So it's been a pleasure. Have a great day, everyone. Hopefully it's been interesting. And I'll see you for the last session about homeostasis and EI balance.